See, my talk is basically a mix of quantum cryptography, modern cryptography, post-quantum cryptography, everything together. Uh, something like nothing like post-quantum cryptography now. The reason is already quantum cryptography is reached. Earlier, 10, 15 years ago, we were telling that that is somewhere there, but now it is there. So I would like to point out what is the recent advances in uh, quantum cryptography, what is happening there, what are the algorithm development, all those things in my lecture today. And this will have a lot of maths, the physics, computer science, all together will be there. Let me start first. Actually, what is the purpose of the cryptography? Cryptography is basically giving these three assurance. One is this confidentiality, integrity, and authentication. And if you look at any crypto system, either that crypto system will be aiming either for attaining the confidentiality or integrity or authentication or together sometimes, but all three may not be possible. We have historically symmetric cryptography, where both sides, that the sender and receiver, are in the same trust. Algorithm like old algorithm data encryption standard, which was in 1977, and it was later improved by double DS, which is broken, and it is next stage is around triple DS. Triple DS was used predominantly till around 2000, and around 2002 or something, this NIST and other agencies started thinking about a new encryption algorithm which can be worldwide used, new symmetric algorithm. Any worldwide, any companies can use. So people develop advanced encryption standard, and there are various versions, at least 3 versions of advanced encryption standard, and almost like 25 years, still that AES is considered to be secure. That 3 versions of the AES is as key length is increased. It can be AES 128, AES 256. Now currently we are all using AES 128. To break the AES 128 with the current standard of computation requires 2 power 128 searches, brute force search. Though some advances are made, but still it never come down from 2 power 126. And totally, truly, some other people think that, okay, we will go for AES 256 because AES 256 requires 2 power 256 searches for breaking. And these are all it's happening in the case of symmetric crypto system. So I think there are many designs came. Along with AES itself, there were 5 more designers there. But predominantly everybody, every industry, every world in the world and everywhere they are using AES. Equivalent to AES, for example, if you ask what is happening in China, they are using their similar version, something called SM4. They are not using AES. But since internet is to be used everywhere, I don't know what exactly the Chinese have a standard called SF family. But all other countries are using AES. See, there is a limitation for symmetric crypto system is that key distribution problem. Because first of all, when two parties join together, they should have shared the key early. But how they will share in the key, all these questions are coming. That is called key distribution problem. If number of participants are increasing, and it's again becoming an issue. For example, NC2, N factorial, NC2 combinations of key distribution is required. This is, we know, when the symmetric crypto system itself is developed. If you look at World War period, initially there was only one crypto system called symmetric crypto system. During 1977 or only the RSA, in fact, initially it came as a Diffie-Hellman key exchange protocol. Diffie and Hellman together developed the key exchange protocol. And around similar time, this RSA came up, reverse Shamir agreement came up with the RSA crypto system, and around 1986 or something. So they wanted to solve the issue of K distribution problem, and also the trust relation between the sender and receiver is in different states. So it necessitated this development of asymmetric crypto system. So RSA developed around 1986. After that, so many variations. You can see 40 years, 50 years from the RSA is developed. Still, people are using RSA. In the case of symmetric crypto system, still people are using AES. So it is almost like time tested, these two. But academically, we cannot say RSA is always, for example, now people started, I think this itself, elliptical crypto system also started around 20, 30, 40 years ago. When, in fact, the idea of elliptical came 1,500 years ago. But how to use elliptical for the crypto system people started understanding when Miller and Koblitz introduced the idea of elliptical crypto system. The advantage of elliptical crypto system is smaller key size compared to AES and efficiency. By efficiency, I mean there are many methods are developed for elliptical crypto system to develop. For example, the elliptical addition, finding the number of points on the elliptical, which elliptical can be used, what is the elliptical random number generator. A lot of research, maybe thousands of research papers came on elliptical crypto system. Efficient implementation on these both RSA and elliptical crypto system in the FPGA circuits. These are all for many years. It is happening, and still people are using it. Then some people say, okay, we want more modification on elliptical crypto system. So something like pairing-based crypto system came. That itself surviving in the world for many years. So basically, these are all under called modern cryptography. This has impact on the SSL and TLS communication, internet communication, and also in cryptocurrency. So as of now, world is predominantly using this AES as well as RSA, elliptical and all. Even in any communication like WhatsApp communication, for example, and Signal protocol, iMessage, online banking, digital signatures, e-governance, contracts, everywhere these crypto systems are used. These are all well studied. Now well studied, and many standards came, and IEEE standard came. For example, RSA standard came. Lot of standard came, and libraries are available. Implementation, best principles of implementation are available. Secure coding practices are available. So now we can say these are all very, very good crypto system which people can use without fear. But this quantum cryptography is that quantum computing is coming, and past 35, 20 years we were telling it will come, but there are some signs that quantum computing is possible. Though current quantum computing, for example, there is the National Quantum Machine, it's happening in India, but TIFR is developing a quantum computer. IIC Bangalore is developing a quantum computer. That number of qubits is only very few, that three qubits or something. With that 3 qubit, you cannot break any public key crypto system. It is only, you can see, for example, if you want to break RSA, for example, what is breaking RSA? Breaking RSA means finding secret key. What is finding secret key? This RSA depends on some mathematical problem called integer factorization problem. There are basically predominantly two puzzles. One is discrete logarithm problem, another is integer factorization problem. Integer factorization problem is, we know the 2 prime number 3 and 5, and you can multiply it easily. 3 into 5 is 15, but given 15, finding what are the prime factorization 3 and 5 is a difficult problem. Multiplying itself is difficult, but finding factor is more difficult than order of complexity is very high. So there is not even a sub-exponential algorithm is available for breaking it as of now for larger prime P and Q or larger size prime P and Q. I'm not talking about RSA 256 or something. I'm talking about RSA 1024. And 1024 means that is two prime numbers with multiply the total bit is 1024. And generally what is happening is if it is about to close, about some attack is coming on discrete logarithm problem or integer factorization problem, then people will increase the prime numbers, size of the prime numbers P and Q large, so that again you can defeat the algorithms for finding integer factorization. So we can comfortably tell that RSA 2048, that is double of that. And one of my professor was usually telling that RSA 2048 can be broken only in 2048. That is another, now it is 2025. Another 20 years is required for breaking RSA 2048. So RSA can be used very well, not an issue. Up to 25 years, not an issue. You just increase the prime size. It's easy. And for example, AES, Advanced Symmetric Crypto System, 256, AES 256 itself is a very large. For example, if you want to break AES 256, you don't have any other method of cryptanalysis other than brute force attack, because all the nonlinear components in the AES is well studied and considered to be nonlinear, are proven to be nonlinear. There is no attack is available on RSA, sorry, AES, differential cryptanalysis, linear cryptanalysis, correlation attack, cube attack. Nothing is possible on AES other than brute force. But brute force given computational power, you cannot do it. Even AES 128 itself is considered to be secure. With current computing facility in world, you can have a 2 power 64, you will able to do it. Not more than that. Okay, so what is the problem then? We are all safe here so far. You need not worry, you can do that. But when quantum computer come, what will do? First of all, there is an impact on the symmetric crypto system. That is called Grover's algorithm. That Grover's algorithm is established in 1996. What is Grover's algorithm is doing is searching an unsorted database of or list of n items. This algorithm will be able to have a speed up of order of n times. All other in general requires power of n. So Grover algorithm will be able to reduce it, root n. In fact, root n is possible, not even n. It reduces the key space further. And what is the impact on the asymmetric crypto system? Asymmetric crypto system, for example, there is something called Shor algorithm is available. Shor algorithm is, if Shor algorithm also developed in 1994, it will able to factor RSA. What it is doing is it will turn the factoring problem into an order finding problem. That is a classical algorithm. Then finding the order using quantum Fourier transform. So that part is a quantum algorithm. Then using Euclidean algorithm and continued fraction algorithm, you can find the factors. Generally, if somebody learn about how to break or how to find integer factorization problem, and you are all using continued fraction algorithm only. So you can see Shor algorithm is also using continued fraction algorithm and Euclidean algorithm to find out it. So Shor algorithm is a mix of classical as well as quantum. What is a quantum? In that is quantum Fourier transform, remaining under classical only. So currently RSA 256. RSA 256, nobody is using it. That can be broken with 4098 qubits. Now, currently we have only 5 qubit or something. So we don't know when you will get 4098 qubit. And by the time nobody is using RSA 256. So you need not worry about those quantum computer which will break RSA now. It will take years and years. But how many years? Nobody is able to predict it. So the research is on that. When you can develop a quantum, how many qubits you can attain so that the integer factorization problem can be solved. Uh, am I audible? I will ask this question again and again.
Yes, sir, you're audible. Yes, sir.
Yeah, fine. Okay. So now I will also move a little bit on the quantum information technology in between, because so far I have not told about what is quantum computing, what is qubit, what is the importance of this. Okay, first of all, I would like to tell that uh, I am also doing some research on the quantum computing, developing algorithms for symmetric cryptanalysis, working with many government agencies on this. So I have some experience on understanding what is quantum computing. Little bit, not high level. And I am basically a math person, uh, trained as a mathematician. So my thought on quantum computing always will be on what is the maths behind it. But if one of you or some of you wanted to work on the quantum computing, you should have a good knowledge on physics and also maths. Maths is particularly linear algebra and little bit on functional analysis. Assume you know these maths and physics, then you required this gate and logic circuits and all those things. Then you required a knowledge of the computer science and little bit on the implementation of this. These are all required to become an expert in quantum computing. Minimal level understanding is required. So I am trying to cover all these aspects today's lecture one by one. I will come back again and again. And also there is another feeling is many people are not familiar exactly what is happening because lack of knowledge in all together in a one setup. So let us learn together in this lecture. See, the quantum information technology, if you look at that, we have quantum sensors are available. For information inputs, we have quantum sensors. This is done. Many companies in India and abroad is developed already the quantum sensors. But for information processing, we required quantum computing. And information transfer and security, we have quantum communication and cryptography. So you can see for the information inputs, sensors, processing computers, transfer and security, you require quantum communication and cryptography. First is can be done. That is quantum sensors can be developed. Quantum communication can be developed. For example, key distribution, QKD distribution and all. Many companies are come up with a solution. And for security, anyway, crypto is there. But for the information processing, we have quantum computers, but we are at the initial stage only. When we will get a quantum computers without error is a question. That will take some time. Simulators are available. For example, Qiskit is a simulator. IBM is claiming to have a quantum computer. To use their quantum computer, there is an interface. Qiskit is available. You can do the programming on Qiskit and run on the IBM quantum computer. It is possible. They are claiming it is there. And in India, some security agencies have, for example, IIT Roorkee and IAC together developed a simulator a few years ago. uh, Under a Ministry of Information Technology project that is called QSIM. That simulator is now working at CDAC Pune. That is a simulator. That simulator is basically a version of the Qiskit. how it is developed, that people may be interested to know, because I have been following the work of Professor Apurva Patel, and from IAC, he gave the idea how they can be done. So such a simulator is available in India. So not quantum computer, simulator is available. Behind the simulator, you required a high performance computing. So this is available, and you people can try on the QSIM with the CDAC Pune. And if you want, you can try with IBM with the Qiskit and IBM, and Google also came up with some simulators. There are one or two good simulators are available to understand that, but a real quantum computer yet to come. Okay, what is quantum mechanics? Quantum mechanics is not new. It is a minimum 100 years old. Nothing new. If you ask any physics person, will be able to tell you what is quantum mechanics. The problem in the quantum mechanics is, it is hard to preserve the quantum mechanical character of a physical system. That was a problem in quantum mechanics. But now people, China and all other some countries are telling they have a technological means to allow the building devices with extreme facility, that temperature, low temperature, very, very low temperature, they are claiming, and that material sciences develops such that you can preserve the quantum mechanical character. I don't know. I'm not familiar. I've not seen that also. One thing I know is the quantum mechanical character, a lot of errors will be there. In fact, I will go to tell about the problem in the error. Okay, so do we have quantum supremacy reached? No, you are not reached. What do you mean by quantum supremacy? With current computational capability, we can do all these things. Whether the quantum computer available which can solve the problem which cannot be solved by a current computing facility, that is not there. If you look at recent NVIDIA's and computation facility, even they are far better. So as of now, quantum supremacy has not reached. But there is a hope that quantum supremacy will become. When, we don't know. That is, quantum supremacy is, there is a computation algorithm is available which cannot be done by this classical computer, GP or whatever maybe, but it can be done by quantum computer at some stage. We don't know when it will come, but there is a hope. That is the reason this government is spending, for example, Indian government is spending 6,000 crores rupees on national quantum machine. Maybe 10 years, 15 years, we don't know. Okay, so what is quantum science? I will come back this slide again and again. You have to understand the concept like superposition and measurement, interference, and entanglement. These words you should understand very clearly. What is superposition? It allows qubits to hold multiple states at once, so dramatically increasing the computing power. So quantum mechanics is using this. Multiple states. A qubit will have multiple states at once. So multiple state definitely will increase the computing power. Measurement. Measurement, see, when you conduct a measurement, and its quantum mechanical character will be lost, and it will become a single output. Multiple output will become a single output. So that is called measurement. And interference, after measurement, state you get is actually random. But random is fine, but there are some probabilities associated with the respective states. And you can tweak this probability. You can increase or decrease for the state we want. This interference is an interesting thing. So once you measure, actually the output is random, but you can have a probability associated with the respective states. And you can increase and decrease the probability also. I will be explaining the maths behind this interference, superposition, and measurement later. And fourth is entanglement. that state of one qubit depend on the state of another, no matter the distance between them. See, Albert Einstein had an issue there. See, actually, these two separated particles remain connected without being direct contact. Nobody could explain why it is called, why it is happening. One particle from here and one particle from that distance. But if one thing is the state of one qubit is depending on the other, even though the distance is very large. So this Albert Einstein was telling about something called spooky action at a distance. Nobody could able to explain. Even Albert Einstein could not explain how it is coming, because particles seems to be communicating faster than speed of light. So that is called entanglement. And the next few points are the debates in the physics, classical physics, and quantum mechanics. Uh, why, how people try to explain what is spooky at distance. For example, EPR, that is called Einstein, Podolsky, and Nathan Rosen. They were arguing that there is something called a hidden variable will be added to quantum mechanics to explain the entanglement. And they were telling about something called locality and causality in this behavior of the particle. Then they were trying to explain locality means what objects are influenced by immediate surrounding. Causality states effect of occur it cause, and that causal signal cannot propagate faster than light. So these type of argument were there, and later Neil Bohr disputed EPR argument. EPR means Einstein, Podolsky, and Rosen argument. And Schrodinger and Fourier finally hypothesized entanglement vanishes with wide particle separation. So this happened. So it will, when wide particles are widely separated, entanglement will be vanishing. And if you look at physics now, Clausen and Friedman in 1972, so they were able to experimentally prove that two widely separated, widely, that time widely is only 10 feet, or 10 feet distance. They say it can be entangled. And see, when trying to increase that length, uh, finally they understood, okay, at least for 10 feet, there is a possibility. So prove that entanglement is very real and fundamental in nature. And if you look at quantum mechanics later now proven to be work, it is working now, even not only at short distance, but greater distance. You might have heard this news about China's quantum encrypted communication satellite called Mikias, and they were proving, we don't know, they were claiming that they could use the quantum entanglement between the photon that is separated thousands of kilometers. We don't know the claim, and this claim they made many years ago. When I started understanding all these things, this local realism, quantum mechanics, I couldn't understand much. Basically, I don't know what. So for me, it is like a religious science. If you look at the internet, you can see what exactly religious science is. So like physics and metaphysics joining together, no idea. And for me, it looked like something difficult, could not understand, could not be explained. Okay, so then I turned to understand what is the maths behind it, so that I would like to know some. I wanted to satisfy myself on that. Okay, later I studied more. Uh, it is not my problem alone. The quantum computing, the feasibility of quantum computing, there was a doubt whether this will happen. This doubt was raised in 1995 itself. You can read the paper by Intro, and the title of the paper is Maintaining Coherence in Quantum Computers. And he warned that maintaining coherence is hard. In 1997, 5 itself, that is error. See, one error in 1,000 computation. Still, this is happening. One error in 1,000 computation. And look at, for example, error integer factorization problem you are trying. A small error. What is the point in finding? You are reaching a situation where you are having error in every 1,000 computation. You cannot work in that. That is a big problem in the quantum computing presently also. Number of errors are increasing, exponentially errors are increasing. So people try to reduce this noise. First of all, trying to understand what is this noise, modeling the noise. See, when people started using simulators or developing simulator, they also try to simulate the noise. Otherwise, it will not work. Okay, real quantum computers, how they reduce this noise? Definitely, first is using lower temperature. But how long? Reduce temperature, reduce. It become crazy. And another is increasing signal, that is bringing particle closer. So these are the only way to reduce this noise. Those who are developing the quantum computer. But for the people who are working on the computer science aspects, there are error correcting codes. There are good error correcting codes exist. But if you want to learn more on error correcting codes, something like quantum zoo, error correcting zoo or something, you can see ZOO in the website. You can see that there are a lot of quantum error correcting codes people have started developing, trying to understand which is it, how you can implement it. All these are happening in the research. These are all research area now. Okay, so why the problem? Because as I already mentioned, the fault propagation, that is if the error propagation will ruin the entire computation. And now there are some people who are doing research on quantum error correcting codes, which is a combination of classical and quantum operation. People are trying to use BCH codes and all these codes, how it can be used. So basically a new, because assume we got a quantum computer, somebody will able to develop, then can you develop a fault tolerant quantum computing? That is a research is happening in this worldwide. So this is about the fault tolerant computing. As of now, any question, or I don't know whether I am audible.
Yes, sir, you're audible.
Okay, fine.
The participants, if you have doubt, you can raise the hands. Then I'll enable your mic.
Okay. Let me continue because a lot of things to be covered. And there are some claims. One claim is 2021 IBM, their machine called Eagle. They are claiming that they could realize 127 qubits. And in 2022, 433 qubits. And 2023, 1000 qubits. And it is based on chip called Condor, which has 1121 qubits. So you can see that the claim is doubling number of qubits yearly. I don't know actually these claims, but it is seen. I have not worked on the IBM quantum. I have not seen also. So these are all I took from the literature, and I heard from what others are talking. I heard lectures of IBM people. I heard lectures of other scientists. They are claiming that they have seen this. And I am working in frequency sensing and similar type of things for the information warfare. This is a part of my project. In one of the project, we were trying to understand how the, for example, breaking this or understanding these communication signals. I also have seen several products of the L3 Harris company. L3 Harris is an American company. They have a division in many American universities also. They are developing a lot of machine like radio frequency sensing and receiving. They have a counterpart in French also. And I saw their website and their brochure basically. So they claim to have developed quantum frequency sensing and receiving equipment. It is possible in my view, because as I mentioned already, sensing and molecular interaction, these type of things are possible in quantum. but not crypto basically. So quantum sensors are developed, and the claim of this company is they were enabling RF convergence. For example, suppose an ordinary receiver, if you want to use an ordinary receiver, um, you may have to tweak or you have to develop a lot of individual algorithm in the case of HF, VHF, UHF communication, LS band, C band, X band, KU band. Even if you look at Starlink user terminal, you require different receivers. That is a problem. But what these people are claiming is because they are using quantum sensors, with a one device, they will be able to do that. So if the claim is true, then it will have a tremendous impact on electronic warfare and tactical communication system. I have not seen their product. I heard the claim, that's all. But it will be interesting for people to understand how the claim, is it really happening, and how the algorithm is developed for sensing. No idea about that. So finally, now, so you can clearly think that there is some movement is happening on developing quantum computer. Some success story is there, but success story will not come in cryptography easily. Success story will come in sensing and all other more that personalized medicine and all those areas. You can expect that some improvement will happen in the case of quantum products, but don't expect easily on crypto will happen, because that is not an interest. Crypto is not the interest of quantum computing. Quantum computing is something else. Okay, but always you can assume that there is a possibility of quantum computer will come, and AES 128. If you look at Grover, if Grover algorithm is available, that will 2 power 128 search will easily reduce to 2 power 64. 2 power 64 you can even break now. So AES 128 will be vanished. Okay, the solution is AES 256. And I saw the developers. I recently, I think 1 month before, I met two scientists. One who developed AES. I asked him, what is the status? Are you increasing the key size? Like quantum computer, why not 256 become higher size? The research is not on that. There is no point in increasing the key size. That is not a wise method of doing. So they are also coming with a new symmetric crypto system, which will replace AES 128 or AES 256 shortly. It will take some time, but there is already some researches happening in European countries are now coming up with a new symmetric algorithm. Okay, so there is a chance symmetric algorithm, improved AES may come, or new version of AES will come. So symmetric crypto system will survive, even though your quantum computer is coming. But a public crypto system, there is a problem. That, for example, if you look at the RSA and LGAML crypto system, RSA crypto system depends on integer factorization. LGAML crypto system during it was developed same time, almost same time, depends on the discrete logarithm problem. So you almost like 20 years of stories. There are some books are also available on the stories of that people how they tried to break RSA, how they tried to break integer factorization problem. If somebody tried to find an integer factorization problem, it is almost near, then whole community will rely on the or depend on the crypto system, which depends on the discrete logarithm problem. So another 5 years, LGAML crypto system will be more predominantly applied. Then people will try to find an attack on the discrete logarithm problem. Then people again go for the integer factorization problem. So last 20-25 years, people were depending on either this or that. But when the quantum computer comes, maybe 10 years or 15 years from now onwards, Without an error, if you can have a computing facilities available, then this both discrete logarithm problem as well as integer factorization problem will be broken. So that means now itself we have to think about the situation that this is broken. That is called post-quantum cryptography. So in the academic world or industry world, you can say, everybody is talking about HNDL, harvest now, decrypt later. So they are all collecting, or I don't know what is that true or not. People are claiming that NSA collecting all ciphertext now. Collecting ciphertext, taking ciphertext from various sources. What they will do with the ciphertext? How they will get the plain text from that? But expectation is take all the ciphertext now, wait till quantum computer comes, then you can break that and you will get a plain text. So the secrecy, there is a problem. Current total high-level secret document, which is secret today, may not be secret after 15 years. So now, if you want to keep the document permanently, you should not use RSA or LGAML or any RSA, LGAML pairing bus or anything. You have to use a new crypto system, which is not depending on these mathematical problems. That is called post-quantum cryptography. The word post-quantum cryptography, the research on post-quantum cryptography all started at least 10 years ago, minimum 10 years ago. And many candidates came, for example, lattice-based crypto system, code-based crypto system, multivariate quadratic crypto system, super singular isogeny. So generally, these are the four paradigms where the post-quantum crypto system has developed. All are maths, lattices based on lattice theory, code based on coding basically, and multivariates computational. Super singular isogeny is based on spherical geometry. So these four people develop many crypto system based on this. Nothing new. The concepts are not new, but many new crypto systems developed and many are broken. Still not standard came, but some people are claiming last year, I think few years ago, people are telling lattice-based cryptography is considered to be okay for that. And next slides, I will be telling about that little bit. Okay, so lattice-based crypto system. At the core of the lattice-based crypto system, the problem are hard for classical and quantum computers to solve. There is something I cannot go deep into that. There is something like short vector in the high dimensional lattice. You have to understand later in 1 hour anyway, you will never understand that. Something like short vector problem, closest vector problem, and shortest integer solution. These mathematical problems you have to understand clearly to understand what is called lattice-based crypto system. And they will provide the security, this LBC. And now the codes are available, libraries are available on various lattice-based crypto systems are available. You can implement it. And if you look at a few, I think 2 years ago, I was in the committee of Ministry of Electronics in India, and they were advising the industries to move from conventional crypto system RSA and those to lattice-based crypto system. There is a transition plan is available, and many companies are started doing that. How to migrate from this? Already, all software companies are doing this. And only the problem with this, okay, what is lattice-based crypto? Advantage of lattice-based crypto system, one is its efficiency and versatile. That much effort is put on lattice-based cryptography now. These algorithms can be implemented with less computation overhead than other quantum resistant cryptographic method. You have seen the other three basically. So the beauty of lattice-based crypto system is this can be easily implemented, and people already started implementing this. And There is a project called Cryptographic Suite for Algebraic Lattices. That project came in 2017. Started in 17. There is an algorithm called Kyber, that is for key encapsulation mechanism, and dilithium for digital signatures. And Kyber and dilithium is in the standard process NIST, but recently it's adopted. It is adopted in industry, but the problem is implementation cost. And for example, banking industry, for in existing infrastructure, integrating this without affecting seamless. These are all the challenges where current industry is facing. But there are solutions are available. Multiple projects are multiple codes are available there. Lot of students, lot of staffs are working on this area, implementing and transmission, adopting to the industry. So I assume that in few years, maybe in maximum 5 years, this will be done. So almost all industry will be using this. That is 100% sure. The RSA and all will not be, people will not be using RSA or anything. This will be used. Why? Because people are expecting that quantum computer will come. So then they cannot change quickly. It requires 5-6 years for transitioning or adapting the industry. And if you look at quantum cryptography in communication protocols, double ratcheting, that is in, so where are these things are applied? And double ratcheting is a method in 2013 it's introduced. If you look at signal protocols or even iMessage, if you're using iPhone, you can see iMessage. Both signal and iMessage using double ratcheting protocol. And iMessage recently few months ago, and they were telling, okay, I'll not go in detail about it. I'll come back. There are some statements like PQ1, PQ2, PQ3, PQ4. PQ means post quantum, level 1, level 2, level 3. The signal protocol reaches up to PQ2, that is second level, because they are using post quantum extended diffie-Hellman. And the problem is they are using public key is ECC based. So it is not PQ3, whereas iMessage, that is messaging in the iPhone, they were again using double racketing, but public key is post quantum. That is, they reached PQ3, but there is a problem in that is still the group messaging and crypto deniability, they are not using it, but for authentication purpose, they are using post quantum. So iMessage till these are all, I think, few months ago. Currently, I don't know what is standard. They reached the level of PQ4. So now you can see that communication protocol, this introducing this post-quantum crypto system is easy. Communication protocol, because they wanted that to be secure. But banking will not take easily. It will take many years. Banking transaction will be used. Internet transactions still take time. But this special purpose communication protocol already reached that level. Now let me tell about more on quantum computing. So what I was giving is only an overall idea. And now let me go in deep. Now a little more physics. If you have any questions, you can tell me. Otherwise, I'll move to the physics, maths, computer science, and all together. Okay. First, we should know what is classical physics. Because we were asking, I was telling now why quantum computer is coming, why not coming, what is the error. All this I have to explain mathematically. So next few minutes till 7:30, I will be telling about this. Basically maths in quantum mechanics. The particle carries, every particle, it will carry with it physical quantities like position and momentum and energy. So any particle will have these three, one position and momentum and energy. And as particle moves in space, and when it is moving in space, when it is interacting with objects, these quantities will change continuously in time. So these are the physical quantities. These physical quantities, once started moving in space, as time changes, this will change continuously. And what are physical quantities? Generally, they are single valued. These physical quantities are single valued. What is single value means? One value at a time, at a given time. One value at a given time. And physical quantities are continuous. Continuous means smoothly changes. So this is a case of classical physics. Classical physics, position, momentum, energy moves in space continuously, basically single valued. By continuously, I mean it is smoothly changes. But and now think about this situation where we are talking about the quantum computing in the case of quantum settings. Quantum setting, it is entirely different. Quantum settings, physical quantities sometimes be discrete. It will be discrete, meaning we can list all possible values it can take. You are able to list all possible values it can take, and never equaling something in between this value. So basically these type of discrete, you can list it in terms of quantum variable. So what is happening is this contradicts the idea of physical quantity must be continuous. Earlier we were telling physical quantity must be continuous, but here we are telling it is discrete. So this is one problem in the quantum setting. And second problem is a particular value we measure at random, but being probabilistic. I already mentioned this earlier. We measure, the particular value measure is random, but probabilistic. This means when we measure, when we are making a measurement, or before we are making a measurement, we do not know which of the possible energies we will get it. But however, we know that some values are more likely than others. So there is a probability attached to each value. So that's what I'm telling you. Before we measure, we don't know exactly what is that. But we know that there are some values are more likely than others. So there is a probability is attached to each value. If we use current quantum computer, for example, breaking some integer factorization, that is 3 into 5 is 15. Today it will get 15 as 3 into 15, but there can be a lot of errors. So you don't know exactly what is the answer for that. So you can make it probabilistically the answer. This is the problem here. When we started measuring, it is a random but probabilistically. And again, this particular thing is contradicting the single valued characteristics. Because what is to call it as a function, you require a single value. Otherwise, you will not call it as a function. So here, before the measurement, we cannot determine the single value for the quantity. So it can be any one of them. So quantum mechanics, continuous function will not work. Will not work. In fact, function will not work. Function requires a single value. Continuous is not there because it is discrete. So you required a new strategy or something new to define to explain the variable in the quantum computing, quantum mechanics. Continuous function will not work. Now we have to define what is called randomness. We have to model randomness. Before we make a measurement, the particle somehow holds an information on every possible outcome we could get. There is an information is inside that. For example, suppose a particle has an energy A. Suppose a particle has an energy A. Let us say that the particle is represented by a mathematical object MA. Is an energy A, and associated there is a mathematical object MA. This MA could be anything. For example, it can be a function, or it can be a simple element of a ring, an algebraic structure ring, or it can be a manifold. Exactly, we don't know. It is a mathematical object. So corresponding to a particular A having an energy A, there is a mathematical symbol or mathematical object is associated with that. This mathematical object we don't know exactly, but there is something. And with the B, there is an MB. With the C, there is an MC. So on. These are all mathematical objects. Now, our particle is represented by, I can say it is a particle in the quantum mechanics is an amalgamation, that is altogether of these mathematical objects. So you have to understand what is MA. These are the mathematical objects. This mathematical object MA, either it's a function, element of ring, or manifold. MB is corresponding to another ring and another energy. NC is corresponding to another energy. So our particle is represented by join of all these. How we can join? I will say I will join with something called a dot product. MA.MB.MC. I don't know exactly. Basically, it is an unknown. I want an unknown way of combining these mathematical objects. But in between, I was telling that the outcomes are more likely. Some outcomes are more likely than others. So in those situations, we should have a probability also to be attached to the algorithm, attached to these objects. So I am trying to attach a probability this is AB, AC, like that. I will use some another operation. May not be I will use dot. I will use many combinations. I don't know exactly what combination I'll be using it. These A, B and all, they are encodes the probability. You can see in one of my slides, I was telling that quantum computing, that a lot of probabilistic value is also coming. I wanted to explain how the probability is coming. So now you look at that an energy, a particle is basically represented by a linear combination of something like a some vector space, A, M, B, etc. I still have not defined what is this operation. It is look like a linear combination of something and now seems to be like a vector space. Now I have to define something called what is the discreteness problem, because I already told there are two things. One is randomness problem, another is discrete problem. In quantum mechanics, I have to tell about what is discreteness problem is also coming here. Here, how to represent our physical system? We already told functions will not work. So we need some mathematical objects allow us to extract the discrete values. We required some mathematical objects which will allow us to extract the discrete problem for that. So I will be using linear operators. In brief terms, I'll be using matrices. I'll be using linear operators, or in brief terms, matrices, to represent the physical quantities. So what is a matrix here? This matrix consists of some discrete set of numbers. We may somehow extract our physical quantities from that discrete set. So now I am able to define a randomness and also the discreteness. So in general, now I conclude that the particles can be represented by linear combination of vectors in some vector space, and physical quantities are represented by linear operators within that space. So now I'm slightly moving to something called linear algebra. Now energy is having three different components. For example, I attach a probability. I now move to linear algebra. Okay, now next is I am now defining two notations which is predominantly used in quantum computing, like bracket notation. Because when you learn something on the quantum computers, people will be starting telling about Hilbert spaces. So I am coming to that point, Hilbert space, why it is coming here. There are two functions, bracket. These two notations, and I'm explaining how to use it. Now you consider a one-dimensional wave function psi. By one-dimensional wave function, I mean this. This is a one-dimensional wave function. For x1, I can use psi x1. X2, I will use psi x2. X3, I will use psi x3. So this particular one-dimensional wave function describes a quantum mechanical particle, and the values are psi x1, psi x2, etc. Where psi x1 and all the function value at the point x1, x2, etc. I can represent the whole function psi in a column vector, psi x1, psi x2, etc. This type of column vector I can use it. And this now once this is there, I will use this vector notation basically. I will use this as psi x1, this as psi x2, and this as psi x3. I can use only three-dimensional plane. This is a psi function, and it is coming like this. It is coming like this, and this its reflection. So there are two ways of I am representing. Either I can represent it as a psi function in this, or psi function uh, in the case of linear algebra in the in the in this setup. Two ways I can represent. And this is a three-dimensional space I am talking. In general, it may not be two-dimensionalized. For example, high energy particle may not able to represent in finite dimensional. You required high dimensional space. So you can see that there are two possibilities, finite dimensional space and infinite dimensional space. Now I wanted to explain something called Hilbert space. Okay, what is Hilbert space? Let me say, what is Hilbert space? Hilbert space is, I will say, complete and where Cauchy theorem is valid. You may be finding difficult to understand what is complete and Cauchy theorem. I will explain simply. A space with the polynomials, for example, x, x square, etc. These are all polynomial. I will use some linear combination of these two, etc. I will go up to infinite dimension. These are all polynomials, x, etc. But finally, this is an expansion of e power x. E power x is not a polynomial. So you are adding so many polynomials. Finally, it converges to a number e power x, which is not a polynomial. So you are having so many other materials. By adding together, you are getting another material here, e power x. And if e power x is not part of that, then this is not useful. So you want e power x is also part of this space. That is any series, its convergence, that is its limit is also belong to this. That is called Hilbert space. Then only you will get a complete space. So when you learn this quantum mechanics, you have to use only the Hilbert space, because you cannot say the limit is outside. Limit is also to be inside. So I am going to tell about more about Hilbert space now. Before that, I want to explain this bracket notation. First, I was telling about this wave function. It can be represented by this, or it can be represented by this. It is not the case that always you have n-dimensional vector space is not required always. You have an example like, for example, spin. I wanted to explain you Grover algorithm, but it will take some time. Spin up and spin up is basically this, and spin down. Spin down is this. The spin up and spin states, which denotes a particle, it's live in two-dimensional Hilbert space. I can say spin up is like in this form, psi of x2, psi of x1, two-dimensional space. Similarly, spin down is another two. So there is always a possibility that two-dimensional Hilbert space is enough for us to explain it. Now let me explain another variable like this is a wave function. 1 minute. This is like a ket psi x1, psi x2. This is a ket vector. Ket vector is basically a two-dimensional vector. Only two-dimensional is there. And another notation I wanted to use is dagger. This is a dagger. I say psi dagger. It is called bra vector. This is ket vector. This is bra vector. And this is always same as the reverse. Reverse. So this is bra vector. This is psi vector. This dagger is generally, it is because you are using the transpose and complex conjugate of this. I will explain that with more clarity. This, it is in fact not psi of x1 star, psi of x2 star, etc. This is transpose and complex conjugate of that. Now I am defining what is called scalar product. Scalar product of two functions, phi dot psi. This is bra vector. Sorry, this is ket vector. Sorry, bra vector. This is ket vector. If you want to take an inner product, sorry, scalar product. Scalar product is basically, if there is a finite dimension is there, we will call it a scalar product. If this is an infinite dimension, we call it as the inner product. But terms will be same. How we will calculate is basically phi of x1 star, phi of x2 star, etc. into this matrix psi of x1, psi of x2, etc. This will become a phi of x1 into this, phi of x2 in this, phi of x into this. And what will happen is it will become something like, sorry, I will write here. It will become something like phi psi, that will a sum of 1 to n terms, phi I star psi I. This is a case of finite dimensional. But if it is an n-dimensional, this will become, this will become integrand, integral phi I x psi I x, not that. But there is nothing like x because it will be valid for all points. So it will become dx phi x psi x. That is the scalar product. But if you mathematically what it is you have two ways. You have a sine wave, not sine wave, you have a phi wave, you have a this. This inner product represent this. This overlap, you can explain by this. This is called now the entanglement. That is, I wanted to define what is the mathematical definition of an entanglement basically in mathematics by using linear algebra. Let me explain one more called, this is about the inner product. I want to explain on outer product. Because I'm going to be explaining the theory called projection. Projection is basically by something called, this is the notation we use for tensor product. And we don't want to, for brevity, we can say it is simply like psi. This is a tensor product. This tensor product will explain the projection of that. If you look at that, it is like a matrix. Phi 1, phi 2. I am talking about three-dimensional. This is psi 1 star, psi 2 star, psi 3 star. If you multiply this, you will get a matrix. Phi 1, psi 1 star. That you will get a 3 by 3 matrices. This will represent the projection. Now, from this, what we can understand is, if psi is in a quantum state, we would be able to extract the possible positions, moments, energies, etc. And we can write that in terms of a function ket, which will be expressed as C1, E1, C2, E2, etc. And if we want angular momentum to explain, it will be like C1, L1, etc. This is the case of finite states. But the problem when it is coming to the infinite state, people could not solve that for many years. But finally, as I told you, that completeness idea of Hilbert space came, then only people able to solve that. Now onwards, we are able to explain this, how the superposition state, how the entanglement, its mathematical structure and all is coming now. Now, if you read the recent research papers, for example, on how the Grover algorithm in the natural settings, for example, they were trying to explain, if you look at a computer science person, he will simply explain that, okay, you have a n, for example, if you take a Boolean algorithm, we require order of n binary queries to accomplish same task. What exactly Grover algorithm is doing is, it is a problem to find a target item with some specific properties in an unsorted database using set of binary queries. You have a database, it is basically unsorted, and you are able to find a target item. This particular algorithm, when Grover decide it is, he has not used computing or something. What he took is, he took a uniform superposition state and then alternatively applied two reflection operators for a number of iterations until the target state is reached. This way, he could reduce algorithm so that the total search can be reduced to order of root n. And we recently understood how this can be modified. That means whether is it robust, this Grover algorithm is robust for several types of modification. We try to understand if the database is spread out in a space over different distinct location. For example, as a vertices of a graph, And can you use Grover algorithm to search in the target item? And we understood that this Grover algorithm even robust enough, and it can proceed from one vertex to next only by along the edges of the graph, and it can be adopted to the search algorithm path efficiently. So there are many people are started doing research on modification of the Grover algorithms, and this for to understand all those things you required all these maths, Hilbert space, vector space idea what I was explained. So I know I have not explained properly. The reason is this is not an easy topic. It requires many understanding on physics and maths. So the whole idea what I introduce is crypto is good, RSA is good, elliptical is good, but when the quantum computer is coming, that is not possible. We need to develop algorithms, quantum algorithms suitable for that settings. Now quantum computer is coming, but where is the algorithm is developed? How you can develop an algorithm for that? You cannot always depend on Grover or anything. You need to modify this Grover algorithm. For example, now we are doing a project on symmetric cryptanalysis. For example, block cipher and stream cipher. Can we develop quantum algorithm for that? To develop the quantum algorithm, it is not like conventional crypto, conventional maths or something. We have to understand these modifications, how the entanglement, all these, what are the new algebraic structure to be used. All these are a new research problem.